All right, folks, I want to take you through some basics to remind you about equations for elevation and horizontal distance when we're using total stations. So I'm going to do some drawings and I'm going to take you through how we write those equations. Most commonly, right, we set up an instrument on a place where we know elevation. We're going to call that elevation 1 at TP1. And we foresight the prism on some new location. Let's call this guy elevation 2 at TP2. And when we do these setups, there's a couple different things that you measured and we would measure. And at these particular points, right, we would measure the height of the instrument, which I'm going to abbreviate HI. We'd measure the height of the rod. And then based on the total station, we would have a little viewfinder here, and that little viewfinder would send out a laser. And from that, we would get SD, a slope distance, and VA, a vertical angle. And that vertical angle is always measured downwards from pointing straight up at the sky, which is 0 degrees. So that vertical angle represents the angle from 0 degrees pointing straight up down to some imaginary line connecting your total station and your rod. So in this drawing, we can actually come up with an equation. We can develop an equation for calculating elevation at point 2 based on elevation at point 1. We always start by writing the elevation where our instrument is. And this is going to be important when we think about using back sights on the benchmark, but for now, we're not doing that. So we start at elevation 1. We're right here. We add our instrument height, HI. We add, because of convention, our vertical distance, which takes into account our vertical angle and the slope distance. I'll give you an equation for that in a second. And this gets us all the way over to our rod height over here, and then we subtract our rod height, and that equation will get us to elevation at point 2. So we start where the instrument is. And in this particular case, we can write our vertical distance as a function of slope distance and the cosine of our vertical angle. And I'm going to come back to that in a quick second. So this is commonly the equation for our foresight measurements. That vertical distance component is sometimes sort of weird, and there are different ways about thinking about this. So vertical distance, I often define as slope distance times the cosine of that vertical angle. You might say, well, is this always true? And I'd like to give you two different examples. So let's say you've got your instrument set up and your rod is much higher up. In that case, your vertical angle that you would measure would be much less than 90 degrees. Let's pretend that that vertical angle is 87 degrees. And let's pretend, just to make things easy, that the slope distance, which represents this red line here, that is our slope distance. Let's pretend that that red line is equal to 100 feet. What is my vertical distance going to be? It is going to be equal to my slope distance times cosine of my vertical angle, 87 degrees. And the number that I get for that times cosine of 87 degrees is 5.23 feet. What does that 5.23 feet represent? It represents the difference between where you are viewing the rod and the location of the prism. And in this case, we would assume that you have to take into account the height of the instrument and the height of the rod, of course, right? But what this vertical distance is telling us is that the rod is higher than the location of the total station. So we would assume maybe that the elevation at the rod is a little bit higher than where you are at the total station. So you'd need the height of the instrument and height of the rod to make that, to verify that. Now, what happens in a different case? Let's say your instrument is set up and your rod is at a lower elevation. Let's say we've got this case. In this situation, again, 0 degrees is up here. My vertical angle that I'm going to measure down from 0 degrees is going to be greater than 90. And let's pretend again. Let's say vertical angle is equal to 92 degrees. Again, let's keep things easy. Let's say our slope distance is equal to 100 feet. So in this case, our vertical distance is going to be equal to 100 times cosine of 92. And that number is negative 3.49 feet. Does that make sense? In this case, because of that angle, you are looking downwards. You are likely looking downwards at that rod, meaning that vertical distance is negative. It is being measured from this hypothetical horizontal line extending out from the site of your total station, and that vertical distance is going down. And so when we use the form of vertical distance, SD cos VA, you are automatically accounting for the positives and negatives. You are automatically accounting for a coordinate system. You might say, what about sine? So in this particular case, what if I just took VD, or what if I said instead 100 times sine of 92 degrees times sine of 92 degrees? I get 99.94 feet. What is this equation telling us? This equation is telling us the horizontal distance. So you can think of sine and cosine as two sides of the same coin. One is always going to get you to a horizontal distance, and one is always going to get you to a vertical distance. All right, so what happens if you are set up on a benchmark? What happens if you are set up on a benchmark? I just want us to briefly look at this example down here at the very bottom of the screen. If you are set up on a benchmark, which is something you all experienced, we're going to say this is TP1, and you are back-sighting a benchmark. You are back-sighting the benchmark back here. And in this case, again, I want to say we always start by writing the equation from where the instrument is. The instrument is at elevation 1. We add our instrument height. We always use a sign convention where we add our vertical distance, which is equal to our slope distance times cosine of our vertical angle. We all then get all the way over to where the prism rod is, and we subtract HR. And that will give us the elevation at the benchmark. But what you probably all found as you were doing these calculations is, where is the location where we know elevation to start? And if you just answered to yourself the benchmark, you would be correct. So we will often rewrite this equation as a function of the benchmark. So I'm going to move each of these pieces to the other side of the equation. So elevation at TP1 is going to be equal to elevation at the benchmark minus the height of the instrument plus the height of the rod and minus the vertical distance. Or if you want to write the whole thing out, elevation at the benchmark minus HI plus HR minus SD cosine of VA. And so when you are taking a foresight measurement and using that to propagate an elevation forward versus when you are using a backsight measurement, you're going to need to think about the form of the equation you are using. I hope this helps. And if you have questions, remember, you can always come see and talk to me during office hours.